When I was on my first interview for an NLP position, the person who was interviewing me said something like, well, I wouldn't hire anyone who doesn't know IBM Model 1 for an NLP position. Well, I did not know what IBM Model 1 was at the time, and I did not get that job. Now, in 2024, IBM Model 1 is far less important than when I interviewed, but it's still important historically. So I want to make sure that you don't lose a job because you don't know about it. And IBM Model 1 is a good place to start our discussion of machine translation because the discussion breaks down the different components of machine translation fairly well. But because nobody uses these models anymore, we're going to gloss over the details with abandon. But it will give you a taste of what these systems were like, and it will prepare you for more advanced systems like phrase-based translation and neural translation. And if you want to know more about these things, I wholeheartedly recommend Philip Kuhn's books on the subject, both traditional MT and neural MT. I'm also basing this lecture on his slides. First off, to learn any sort of machine translation model, you're going to need some parallel data. They're called parallel data because you have English on one side and French on the other, for example. And this isn't just for machines. We only came to understand Egyptian hieroglyphics when Jean-François Champollion produced the first transliterations from the Rosetta Stone because it had Greek and Egyptian versions of the same text, a parallel text. But thankfully, there are people producing parallel text today. Some newspapers, people with multilingual web pages, and parliaments of places like Canada and Hong Kong that require all parliamentary debate to be available in multiple official languages. This allows you to decode these foreign languages. And guess what? You know that decoder we keep talking about in natural language models? This is the OG decoder. I'll be showing you a bunch of equations in a bit, and because these models were made by Americans at IBM, International Business Machines, although Fred Jelinek was born in Czechoslovakia, we're going to be talking about translating foreign F text into English E text. And to emphasize this direction of translation, we call the foreign language the source and the English language the target. So the first step is to look at a bunch of parallel data, find all of the translations of those words, and then create a maximum likelihood estimate of those possible translations. But wait! Parallel data don't tell you which word to translate to which other words. For that, you're going to need an alignment. An alignment tells you which words in the English text line up with which words in the foreign text, F. But you don't always have beautiful, perfect alignments like this. Sometimes you have words coming in different orders between languages. Sometimes a single word in the foreign language becomes two words in English. Sometimes words are dropped, and sometimes target words can't be aligned to a source word, and so they get aligned to this null thing instead. So all of these considerations need to be accounted for. So we can now build up the probability expression for IBM Model 1. For each of the English words, it needs to be generated given the source word that it's aligned with. So you look up the index of the aligned foreign word, then find the translation probabilities for that word. Then you have to take into account the alignment. Every English word can be aligned to any of the foreign words or the null token. That's why you have the +1. And then the total expression has an epsilon term for normalization. So here's an example. We have 4 + 1 German words, 4 English words, and then we can compute the lexical probabilities for each of the tokens in this product here. But there's a problem. We have a model with alignments and lexical translation probabilities. If we had one, we could easily compute the other. But initially, you don't have either. Now, maybe you could bootstrap the probabilities with a dictionary or something, but you don't always have that even. So the solution, in IBM Model 1 at least, is to use something called expectation maximization. Take a guess of what the lexical translation probabilities are, compute the expected alignment counts, and then use those expected counts to update the translation probability parameters. Then repeat until it converges. So initially, you don't know anything. All alignments are equally likely. But then you update the translation probabilities, and you see that sentences with la in French often have the. Then after the steals some of that probability mass, then fleur needs to be aligned with something else. Flower's the only thing left. That then gets reflected in the word translation probabilities after another round, then alignments become even clearer. And after things converge, you can read off the word translation probabilities. Here's an example of how this evolves for a toy example. We have the words as rows and each iteration of EM as the columns. Initially, the probabilities are uniform in the initial distribution, then they become peakier and peakier until it gets it perfectly right. However, this doesn't happen in practice because data are noisy and language is messy. So another problem is that this model isn't good enough to actually generate fluent output. It's a little like the exercises that you get in Duolingo. You know which words need to be in the output, you know which target words align with which source words, and then you need to kind of figure out the correct word order in the fluent output. So the way the old models did this was using something called a language model. You might have heard of it. And a way of thinking about this is as an application of Bayes' rule. Check the video in the description if you need a refresher. If you're looking for an English sentence that has the highest probability under a language model, then multiply that by the IBM Model 1 probability of turning the English sentence into a foreign language sentence. This is your problem for decoding foreign text into English. But if you're following the math carefully, the equation is missing the denominator p of f, which should be there if you were using the full Bayes' rule expression, but we often ignore it because we're not searching over the source foreign sentence. It's given, so you can think about this as being probability 1. Note that this math is backwards from what the system actually does. The system is turning foreign sentences into English, but the mathematical model is turning English sentences into foreign sentences. Another way of thinking about this is as a noisy channel model. When people produce a sentence in any language, they first form the sentence in English, then they corrupt it with a translation model, and then produce the foreign output. The machine translation model undoes this process to find the original English sentence. Now, this imperialist mental model is obviously wrong, but it's mathematically convenient for our search. Today, we're only talking about IBM Model 1. IBM had a couple of successor models that explicitly modeled how words got reordered in the translations, i.e., in what way do words move and by. It also explicitly models fertility, how many words on one side of an alignment get aligned with the other side. But once you get beyond Model 3, they weren't used as much, and they weren't worth the computational complexity. Nevertheless, it's still worth learning about the history of these models because these are models that are fairly simple and, at least for closely related languages, actually work. And in addition to working okay, they introduced a lot of useful ideas like a generative model of language that we have come to know and love in neural language models, and combining both learning about a language via a raw language model and combining that with task-specific modeling. While modern models do this with pre-training and fine-tuning, you can clearly see the beginning of the process here. And finally, the alignments should also remind you of the attention patterns in neural machine translation. Warning, however, alignment in these sorts of models means something different. Alignment in language models, Muppet models, whatever you want to call them, means something different. Alignment in that case means getting the model to do what the user wants. Alignment in machine translation is just the word-to-word matching between source and target. So hopefully this trip down memory lane was helpful in understanding the history of machine translation, modeling source words aligned to individual or multiple target words. But there are times when the context constrains how you translate a word, and the IBM models leave all of that to the language model. And we'll see both how the next historical models, phrase-based translation models, deal with this issue, and what extra steps we need to take to deal with this in more modern models. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.